In this video, we're going to take a look at alternating series. In particular, we're going to define what we mean by alternating series, look at a few examples, and introduce a way to determine whether such a series converges. By an alternating series, we simply mean a series which has terms that alternate between positive and negative values. Here we see three examples of alternating series. The first example is the sum n equal 1 to infinity of negative 1/2 to the n minus 1. If we write out the first several terms of this series, we see that we're computing 1/2 minus 1/4 plus 1/8 minus 1/16 plus 1/32 minus 1/64, etc. And that each of these terms alternate in sign. First term is positive, the second term is negative, the third is positive, and so on. The second example here is the sum n equal 1 to infinity of negative 1 to the n times n. And here the terms alternate in sign, starting with a negative value of negative 1, then 2, then negative 3, then 4, then negative 5, then 6, then negative 7, and so on. And our last example is the sum n equal 1 to infinity of negative 1 to the n plus 1 all over n. And here we also have an alternating sum starting with a positive value of 1 and then negative 1/2 plus 1/3, negative 1/4 plus 1/5, negative 1/6, etc. Although we're only looking at three examples of alternating series here, we can see a key aspect of their structure. Each of these series can be written as negative 1 to some power, either n, n minus 1, or n plus 1, multiplied by some other term which is positive. In the second and third examples here, that's made explicitly clear. The second example is negative 1 to the n times the positive formula n, and the third one is negative 1 to the n plus 1 multiplied by 1 over n, which is always positive. In the first example, we could always break negative 1/2 up into negative 1 over 2 and raise each of those individually to the n minus 1 power. And so we could think of that as negative 1 to the n minus 1 divided by 2 to the n minus 1. And then the 2 to the n minus 1 in the denominator is a positive term. To make this idea more explicit, we're going to state that any alternating series can always be written in one of the following two forms. Either the sum n equal 1 to infinity of negative 1 to the n plus 1 times b sub n, where b sub n is a non-negative term for all n, or as the sum n equal 1 to infinity of negative 1 to the n bn, where again b sub n is some non-negative term. These two different forms are very similar. The only difference is whether the first term in the series is positive, as in the first case, or negative, as in the second. As we'll soon see, sometimes looking at the terms b sub n, which is the positive part of our term without the alternating sign, will be helpful in determining whether our alternating series will converge or diverge. To get a sense of how this might work, let's take a look at the convergence and divergence of the three alternating series examples that we saw just a few minutes ago. The first example that we looked at earlier was the sum n equal 1 to infinity of negative 1/2 to the n minus 1. Looking at this series, in particular the form of our term, we notice that this is a geometric series with a equal to 1 and r equal to negative 1/2. From our previous work with geometric series, we already know how to determine if a geometric series converges or diverges. We simply need to look at the absolute value of the ratio of the series, which in this case is the absolute value of negative 1/2, which is 1/2, which is less than 1. And whenever we have a geometric series where the absolute value of the ratio is less than 1, we have a convergent geometric series. So this series here converges. Notice, however, we really didn't need to know that this series was an alternating series in order to determine that it converges. We simply needed to know that it was a geometric series and what the ratio of that geometric series was. Once we knew that, this analysis was fairly straightforward. The second example we looked at earlier was the sum n equal 1 to infinity of negative 1 to the n times n. In this case, notice that our b sub n is just the formula n. We're having the alternating sign, negative 1 to the n, all multiplied by this positive term n. Here, if we want to determine the convergence or divergence of this series, we could look at the limit as n goes to infinity of b sub n, which is just the limit as n goes to infinity of n. And this is one of the easiest limits to compute because we want to know what happens to n as n gets very large. And of course, that means that that answer is that n gets very large. And so this limit is equal to infinity, or it diverges to infinity. And in particular, this limit is not equal to 0. And so what we then know is that if we throw in an alternating sign, like negative 1 to the n times b sub n, that this limit will not exist. The only way an alternating sequence will have a limit is if the terms without the alternating sign go to 0. And whenever we have a limit of terms that do not go to 0, and we make the signs alternating, that limit will not exist. And so that tells us that our series that we have at the top diverges by the divergence test. The divergence test says that anytime we have a limit of the terms of a series that do not go to 0, the series will diverge. And as we see right here, the limit of our terms of this particular series do not exist. They're going to get alternately very large or very negative. Again, notice that we really didn't need to know much about the alternating sign here to determine the divergence of this particular series. We simply need to just notice that the terms themselves do not converge to 0 as a sequence. The third example we looked at earlier was the sum n equal 1 to infinity of negative 1 to the n plus 1 over n. We really don't have any tools at this point to be able to handle a series like this. We can look at the limit of the terms, but we can see that the limit of the terms will equal 0, and so the divergence test doesn't apply. This series is not a geometric series, and so we can't use anything about geometric series. We cannot use the integral test because this sum is alternating, and the integral test requires the terms in our sum to be positive. And the same goes for the p-test and the comparison tests. Those tests all require positive terms. And so here we have this alternating sum and no applicable test at this point to analyze it. And so it would be helpful if we had some sort of test to handle the convergence for alternating series, and conveniently we have one, which we're going to call the alternating series test. So the alternating series test says that if we have an alternating series of the form n equal 1 to infinity, negative 1 to the n plus 1 times bn, or the sum n equal 1 to infinity, negative 1 to the n bn, then the alternating series will converge if the following three properties hold. We need the term b sub n to be greater than or equal to 0. We need b sub n plus 1 to be less than or equal to b sub n, which is another way of saying that the terms must be decreasing so that each term is smaller than the previous term. And we also need the limit of the positive terms to go to 0. And so we need an alternating sum of positive numbers which decrease and have a limit equaling 0. And if all three of these properties hold for our given series, for our given alternating series, then this test tells us that the alternating series will converge. One important note here is that this is only a test for convergence. So it tells us that our series converges if these three properties hold, but it does not tell us anything about when the series might diverge. And so if one of these properties fails, then we're going to have to use a different test to determine divergence. So now that we have the alternating series test in our toolbox, let's revisit the sum n equal 1 to infinity of -1 to the n plus 1 over n, which was the example of the alternating series earlier that we couldn't determine convergence for. In this case, notice that we can rewrite our term as -1 to the n plus 1 multiplied by 1 over n. Right? And therefore, b sub n in this particular series is going to be the formula 1 over n. And so in order to see if the alternating series test applies, we need to determine three things about the formula 1 over n. The first thing is that we need to show that it is positive, and that is certainly true because n will be a positive number here. And so 1 over n is certainly going to always be positive. We need to show that these decrease, and so that means we need 1 over n plus 1 to be smaller than 1 over n. And here we have two fractions with a numerator of 1, and that means the one with the larger denominator will be smaller. And so these terms definitely decrease. And we also need the limit of these terms to go to 0, and that is certainly true. As n gets large, we have 1 over a very large number, and that will get closer and closer to 0. And so all three of these properties hold, and so this particular series will converge by the alternating series test.